because this tutorial is about Poisson models, so let's go ahead and deal with our count that has coughs. So we are going to load these libraries. We have included GLMMTB for Poisson mixed effects model, GLMM-TMB. So we go ahead and load these libraries. So first of all, we are going to do a regression analysis. We are now going to fit our models, see which model is perfect, interpret the models, and we see how to analyze this kind of data. So a GLM, like I said, a GLM has no use here. Although we can look at it, I have used the day as a continuous variable because this is a GLM still. We assume that the days as they continue, they give the same effect. So you see it is significant. It gives a negative slope, which means the coughs decline. And according to site and the IDs are not declining. It's not estimate is not declining. So we can see that the AIC is this huge. So the dispersion is 287. This is an over dispersion. So that means we can try out a negative binomial and we see. Oh, before a negative binomial, we can scatter the GLM Poisson residuals. Ideally, these residuals are not supposed to have a pattern and they are supposed to be concentrated around 0. That's why I added this dotted line going through a 0. So if we try out the negative binomial, it uses the library of mass. So still we can see ID, the cough, they don't reduce, but they increment at a very slow. I think this is like 0.8% per day. And you can see that it cough reduces, the days reduce, the cough reduces the days goes on, and if you even within the study sites. The dispersion is let's see, the AIC is smaller at least for this, and the negative 2 log likelihood is this one, comparing the both. So the dispersion for this negative binomial, you see it is small, negative binomial, but the interpretation of negative binomial and the Poisson in a GLM, they change. A Poisson, it gives a rate, while a negative binomial, we still get our outcome as counts. That's the difference. So we can plot also the residuals for negative binomial. You see they are scattered widely, yet they are supposed to be concentrated around 0. So this also shows that it's not a perfect fit. Even if we didn't know the correlation structure, we didn't check for that, you can see the model has just rejected it. So here we go to another one, which we call a random intercept model. So the random intercept, these are now the mixed effects. So the mixed effects model, actually, I can just include mixed effects models. So, and we start with the random intercept model. Like I said, a random intercept model allows the intercept to vary across groups and all subjects. This means that each group or subject has its own baseline level of the response variable. It means each group has their own baseline cough frequency, but the effect of predictors is assumed to be constant, which is not okay for our case. So this means that for the fixed effects, the day is the fixed effects. The effect of day, or the time, this is the time on cough day is the cough frequency or our outcome, is consistent across all sites and individual. So the effect of, it assumes that effect of time is consistent across study sites and individual. Yet this is wrong. So we have already seen that the cough from the spaghetti plots, that individuals' cough frequencies go down as time progresses. So let's go ahead and we shall go ahead and fit this model though. So we can fit this model. We have now used day as a factor variable to take account of that time effect of day. And the p-values are significant for most days. And it only says that co-frequencies decline at day 11, day 13, and day 14. That's what it says. So we can go ahead and extract the fixed effects and we exponentiate them to see the hazard, the IRR, or the rate, the incident rate ratio. So this is the incident rate ratio for each day. So we can plot the residuals for this. The residuals tend to concentrate around 0, but you see there are these other overly dispersed residuals. So now let's go to the random coefficient. So a random coefficient model, also called a random slope, which allows the intercept and the slope to vary across groups of subjects. This means that each group or subject can have its own baseline, which is true. Each subject has their own baseline level and its own effect of the predictor. Yes, it means that, for example, age can affect this individual as an individual. So the fixed effect is there. Here is going to have the issue now. The overall effect of day on cough is a random, the overall, the fixed effect is the day, which means the overall effect of day on cough is fixed, which is not correct. So the random effect is the day and the time, and the site, but not the individuals. This is where we have the problem. This model allows for variability in baseline cough counts across sites and variability within both baseline cough counts and effect of day across individuals. So this model, you see, this is the model here. It allows you to fix day or time and the site, to nest day and site. And it means that it's only the individual, these are the fixed effects, and only the random these are the day is the fixed effect, and random effects is only day and site. It allows only the variability only in day and site. It means that it allows every individual to have their own co-frequency on a specific day and a given site. However, it does not account for the effect, the random effects within that very individual himself. That means this cannot work for us either. So, but however, we are going to run this model and we see what it brings. So we are going to, we know this theoretically that it can't help us, but this is not what we want. But again, we are going to test it using our statistical tests and the residual plots to see if really what we have theoretically is what the statistics are going to tell us. It is taking longer. I don't know why. Maybe it is a strong model, or I have a weak laptop, one of the two. So I'll go with a stronger model. It is taking time to converge. Another thing to allow this model to converge, to not take a lot of time during to converge, you can allow to have iterations. You can set the number of iterations maybe to 10,000 or to 1,000, such that it stops on those iterations and it converges from there. But now it's going to take a lot of iterations on its own, such that it converges this model. Yeah, so let's give it time to converge, and we can go ahead. I hope it won't take a minute. So what was I explaining? So the second kind of model is going to be the random coefficient model by ID and time. So here we fix day, or the effect of day on cough, and we give the random effects as a site and ID, and both day and ID. So it means that both the intercept and slope of day, which is the days from 1 to 14, can vary across individual. It means each individual can have their own frequency at a given date or at a given day. And they can also have their own baseline cough frequency and their own effect of the day. They can also have the effect being catered for within the study sites that they are in. So this is why we need this. This is the model that we wanted. So we wanted the model that is going to fix this part and then makes this a random. So this is going to be, we assume that the cough frequencies change per individual, that's the ID, and also changes within the day itself. So time has an effect. It assumes that time has an effect on the cough frequency, and also the day has an effect on and also the ID has an effect on cough frequency. This is what we call the between and within differences. Within, that's within the person, that's the ID, and between can be between site and between day. So yeah, this model is finished. It shows that the decline starts at day 7, and however they are not statistically significant. And when we go ahead and we plot the residual plots, we can see it also still has those random residues up here. So let's go ahead and fix this Poisson model. And I hope this one is not going to take long. Yeah, it hasn't. You see now how this is perfect for our data. Almost every point is around 0. Those who are below, they are just within -1, as compared to this one where it even goes to -20. You see? So statistically, all by doing a statistical test, we see that this is the best model for our data. And when we do the ANOVA test, we can see also that the chi-square is statistically significant for the random coefficient model, which is this one we have said. So yeah, if we go ahead and do the AIC and BIC, still we can see that this one has the least AIC and BIC. Still, this random effect coefficient model TMB is the best. So now, how about the GEE, the generalized estimating equations? How do they differ from GLMM models? So GEE models are fixed effects like day, but it assumes that the effect is consistent across all observations. GLMM models have fixed effects like day, but allows the effect to vary across the groups or within the subjects. So that's the difference. GEE models fix the time effect, yet these GLMM models make the time, fix the time, but also allows it to have random effects between individuals or the between and the within subject. But again, let's try it and see what does the statistics say. Let's fix the GEE model. Yeah, this is the GEE model. Let's okay, this is our, let me go straight to the AIC and BIC. This is for GLMTB, and this is our plot for GLMTMB, and this is the residual plot for the GEE model. You see that it is wild. It has these residual plots, even they have a pattern of going up, which doesn't deal with our data. So we remain as the GLMM-TMB model as our model. So so what do we do next? Because we have identified the model, we have the data. What next? So what next? We go ahead and test the assumptions of longitudinal data. So the assumptions, we have the effect of time. That's we have also the effect of the individual effect, and we also have the interaction, the time interaction effect. So we have to test all those three hypotheses. So for that, we have seen from this model, this is our GLMTB, that all right, so that the difference, the co-frequencies start to decline from day, which are significant, start to decline from day 4. The co-frequencies that are significant start to decline from day 4. This already shows that the effect of the time is already established. It goes down. So we go ahead and establish now the effect. We go ahead and make this day numeric, since it's going to be acting as our fixed effect, and then we see what happens. So we have fixed our day. You see the overall effect is this one, negative 0.19. These are coefficients, by the way. If we want to get the incident rate ratio, we can exponentiate these effects. So this is the overall effect of time on the outcome. It reduces by almost 19% if we are considering coefficients. Now, okay, these are just variables categorizing age and so now let's look at okay, this is still the same. Okay, now we have included all our other independent variables, all the predictors. We have age, category, diabetes status, HIV, BCG scar, sex, and let's see how this works. We can see that BMI is statistically significant, the gender is statistically significant. This one is not, but we can also include it in the multivariate. But you see that this is a fixed now. This is now a fixed term. It is 0.19, although we have included we have included the other coefficients, but it's a fixed term. Like you see, it's the same measure. So this is the good thing around these models. You can test the assumptions as you want. So let's go ahead. This one's just to exponentiate to give the incident rate ratios. This was the estimate. This is the exponentiated estimate. You see it is 0.84. It is reducing. This is the incident rate ratio. The incident rate ratio now says that let's go. Those who are diabetes, they have 3.6 fold or 3.6 times more co-frequencies compared to those who don't have diabetes. That's what it means. So something like that. That's how we interpret these coefficients. If it is less than 1, it means it's a protective factor, and if it is more than 1, it means it's a risk. So yeah, we can go ahead. I think this is the same thing. This is the same thing. We are summarizing this. You see that as day goes on, the co-frequencies, the rate of co-frequency reduced by 18%. So as day goes on, for those with diabetes, they increase by 3.6-fold. So what do we do next? We do the time and site interaction. So the time and site interaction gives us if there is any interaction between the time and where this person is taking the medicine from. For example, we have 2 study sites, and our time and study interaction we hadn't included it. It is here. Our time and site interaction, where is it? Time and site Mulago. We have day site Mulago is not significant, but the time and actually none of the interaction terms are significant. But to do that, let's remove we can do that by removing we can first remove the, let's get this code. I'm going to tell you what I'm doing. So let's do one by one. So let's first remove other interaction terms, and we only include the site and time. So if we include only site and time, it is not statistically significant still. Yeah, that means there is no interaction between the study site and the time. So we can go ahead and do this with sex. There is no interaction between sex and time is also not significant. So that's how we go ahead and look for the interaction between covariates and the different and time, the interaction between the covariates and time. So if we want to do bivariate analysis, we first look for these interaction terms, and we maintain only variables that have significant interaction terms. Remember, if a variable has a significant interaction term, it means it stays in the model. If a variable has a significant interaction term, it stays in the model, even if its main variable, the main variable, is not significant. But if the interaction term is significant, it stays in the model. So we go by this, then add all the variables. We do a backward elimination method using by removing the non-significant p-values until we remain with the final model. We test for confounding, and that's how we get our final model. I hope this was helpful. I'm going to leave a link to this error code. You can modify it according to your data. Unfortunately, I'm not going to give you the data set. I might if many people request for it, but you can modify it according to your own data set. Since this is a study that is ongoing, I can't expose the data to the people. So I'm not going to give the data set out right now. But you can modify according to your data. Thank you very much. Please subscribe and give us a like. It will help us grow. Thank you.